So yesterday we dealt with some ramps that were frictionless. Okay, so today we're going to include friction. Tomorrow you will get a chance to do some work. I sort of wanted to build up to that kind of thing. So there will be a work period scheduled tomorrow.
No school Friday.
No school Friday. Again, where there's no school? Oh, I don't know about that. No, I got some labs coming up. We're going to start. Yep, we got some good labs coming up. Trust me. Am I not a trustworthy guy?
No. Haven't proven yourself yet.
Harsh critic. Thanks a lot, subject. So, what is friction? And again, feel free just to, if you want to just jot down little bits and pieces, that's fine. I'm not going to send the note police after you to write everything down. But I do need to tell you, what is friction? Obviously, a force that resists motion involves objects that are in contact with each other. There must be some form of contact. And that's sort of the idea of like a hovercraft or like air hockey table, right? When you put that layer of air and an air hockey table in between, you reduce the amount of contact and you reduce the actual friction. And it's a lot of fun, right? Okay. Some causes of friction. An object deforms a surface and vice versa. So believe it or not, and now there's a lot of discussion still about friction. Some people believe that, like in my calculator here, I put it on the table, there's obviously some friction, that's what slows it down. Some people will say that the calculator actually makes a little sort of bowl shape on the table, that kind of thing. Seems a little unlikely in that sense, but I guess if it's heavy enough, there's certainly that happening. So a plowing force is required to move the object over these deformations, sort of up that side of the bowl. Irregularities interlock and offer resistance to movement. The table itself, right, is not going to be, perfectly flat. It's going to have little humps and bumps to it, right? And the calculator itself, it's going to be like that, right? It's going to have little ridges, little bumps that are going to sort of interlock with one another, right? When you take sandpaper to wood, basically what you're doing is you're taking off all those irregularities, those little bumps, right? You're smoothing it down, and you're actually reducing friction. Now, oddly enough, if you smooth it enough, you actually get to the point where you're actually increasing friction. Why do you think that might be, Jeff?
I don't know, you can only take it down so far.
Hey?
I don't know, you can only take it down so far. I don't know.
Well, what happens is you create a vacuum, and air pressure will actually, because the surfaces are so close to one another, you actually create a vacuum, and then the air pressure will actually hold it in place, kind of thing. That's one thing. There's also that the molecules are actually so close together, there's actually intermolecular forces that are doing that as well. So you should know the difference between starting friction and sliding friction.
Go back.
Go back?
Yeah.
You need to know the difference between starting friction and sliding friction. Starting friction is the maximum frictional force between stationary objects. So when you are ready to push something, right, it's at rest. When you push, it's starting friction that is there. That's the maximum frictional force. And then once you get the thing moving, then you are moving into sliding friction, the frictional force between objects that are sliding with respect to each other. Now we're not talking about rolling friction here. That's something a little different. Okay, so rolling friction, I was actually at a PD session many, many years ago. Rolling friction actually is more like starting friction. It's a little bit, the theory behind it is a little bit higher sort of than high school kind of thing, so we're going to sort of ignore it. So anytime you have an object moving, you can assume that it's sliding friction, but just be aware that in the future you're going to have to deal with rolling friction if you're taking university physics. And it's a little bit different, that's all. Okay, so when we're rolling balls down ramps and we're running the Hot Wheels cars down the ramps, it's technically rolling friction. We'll refer to it as sliding friction. Okay, close enough for our purposes. If you were silly enough to take university physics, right? Okay, some properties of friction. Friction, I don't know. I don't think you need to write these all down. I really don't. I really don't. I do think you need to take your earphones out though.
Wow.
What do you mean, why? So you can hear me.
I can hear you fine.
Come on.
Come on, Mr.
A little more respect. Jesse's been doing it for like the last 10 minutes back there, but I've been debating taking them out.
Mr. Bennett.
Friction acts parallel to the surfaces that are in contact and in the direction opposite to the motion of the object or to the net force tending to produce such motion. So what I'm saying there is that friction is basically always opposite the motion or the intended motion if there is no motion, right? Like if I just push on the filing cabinet, there's no motion, but there's obviously friction, right? Okay? And it's always parallel to the surface. Okay, so those are the two things. It's parallel to the surface and it's opposite the motion. Okay? Friction depends on the nature of the materials in contact and the smoothness of their surfaces. Okay? So the friction between, say, a rubber tire and concrete is actually different than a rubber tire on asphalt. Okay? And obviously the smoothness of their surfaces, Teflon, very smooth, low friction, right? There's always two objects that have to be in contact with each other, so it depends on how rough each one of those is, right? You got like Teflon on ice, like if you're out curling, obviously very low friction. If you've got Teflon on gravel, not so slippery. Sliding friction is always less than or equal to starting friction. Starting friction is always the maximum, and I forgot a couple slides back, but sliding friction is sometimes referred to as kinetic friction, and starting friction is referred to as static friction. Well, just like static electricity is electricity that doesn't move, okay? So starting, static, moving, kinetic. You guys remember what the symbol for friction is? The little sort of Greek letter? The F? Thing. Yeah? Oh, no, that's magnetic field strength. Here's a bit of a controversial statement. Friction is practically independent of the area of contact. In other words, it doesn't matter how much surface area there is. Now, we're not talking about air resistance here. We're talking about like two things sliding on one another. So the most common example that I can give you is just a book sitting on a table like this, right? Obviously, this has more surface area than the edge, right? So if I slide it like that, there's a certain amount of friction. If I slide it like this, if I could balance it like that, friction is the same. Why is the friction the same? Because of the weight, exactly. It's got to do with the normal force, and the book hasn't suddenly, the mass like that is the same as the mass like that, right? What has changed is the pressure. There's no doubt about that. We all know, being Canadians, we know that if you're on thin ice, you need to sort of spread out. That reduces the pressure. Same idea here, but it doesn't actually reduce the friction. Okay, it's a different idea. So practically independent of the area of contact. And if you want to just draw a little picture in there, right, it would be something like this. Right? I guess I have to make it 3D to make it make sense. Okay? So whether the box or the book or whatever it is flat or upright, the friction is the same. Now, I bet you there's going to be another line coming right in there, isn't there? Number 5, starting or sliding friction is directly proportional to the force pressing the two surfaces together, and that is basically the normal force. I'll give Courtney another chance. Do you remember the formula from grade 11, Courtney, that has friction in it? If I gave you the letter, if I said mu equals, remember? No? It's fine. It's not. It's kind of an obscure one. Yeah. Okay. The coefficient of sliding friction is the ratio of the force of sliding friction to the normal force. And that's what we use. We use the Greek letter mu. It's a funny looking U with a tail on the front and the back. Like that. Mu equals FF over Fn. Okay? Mu equals the friction force over the normal force. And you'll be seeing lots of that. You would really hate me if I made you write out that whole question, wouldn't you? Justin said he didn't want that sheet, so I'm going to make him write out the question. Okay, so yeah, you got the sheet there with the question on it, just to save you a little bit of writing. You're welcome. So here we have a box weighing 450 newtons. Now, every time I get to this in the course, I always say to myself, I've got to fix that because boxes don't, well, boxes do weigh 450 newtons, but I mean, most of the time that you are given the mass, so I should probably adjust that, whatever. So we've got the box weighing 450 newtons, it's pulled along a level floor at a constant speed. Now, when you see the words constant speed, that is a sign for celebration, because that means things are a whole lot easier. Okay, and I'll explain that right away. So it's a constant speed by a rope that makes an angle of 30 degrees with the floor as shown. If the force on the rope is 260 newtons, what's the horizontal component? What's the normal force? And what's the coefficient of sliding friction? And I think you do have to draw the picture, it looks like, right? Okay, so I'll give you a second there. All right, so when I'm asking for the horizontal component, what am I really looking for here? I'm looking for that there, and this is the vertical component, right? The horizontal component is the part of the force that does what? Actually makes it slide sideways. And the vertical component, now what does it do? There's some force upward. What does it do, Chris? It's not pointless. What does it do to the box? And now, it's not a hard question.
Makes it up.
Just lifts it up, right? It's just an upward force, that's all, right? Now, if you're trying to slide something heavy, like a big filing cabinet like this, would it help if you could somehow just sort of lift it a little bit? Right? It would make it easier to slide, right? What's really happening there? Okay, well what's happening is that you've got this vertical component, you're lifting it up, you're actually reducing this 450 newtons of weight force. You're making the force between the filing cabinet and the ground, you're making that less. And because of the formula, mu equals FF over Fn, right? If you reduce the normal force, right, the frictional coefficient is based on how rough those two surfaces are. That's set. That's a constant. Okay? Mu equals FF over Fn. So if the normal force is reduced, if this number has to stay the same, what has to happen on to FF to make the FF over the Fn be the same value? Well, FF has to be less. You reduce friction. By lifting up on the object, you reduce the frictional force because the frictional coefficient must remain the same. And I'll explain that again in a specific situation later. Okay, so here's your solution. Okay, so the first thing you're going to do is you're going to find the horizontal component. Remember, it's always cosine. So it's 260 cos 30, or 225. Okay, so to find the normal force, okay, actually, I got things a little bit backwards here. Let's go back to this one here. Do this one on the left here first. Since it's moving at a constant speed, okay, remember I said that the constant speed thing was going to come back to be a good thing. Since it's moving at a constant speed, that means that the friction force must equal the horizontal component. Okay? And I'll just draw it over here for you. You've got horizontal component there. I don't have the friction here, right? But because the object is moving at a constant speed, that means that the horizontal component and the frictional force must be balanced. Okay? So that means that my friction force is 225. Now the second part is the normal force, Fn, is the difference between the downward force of the block's weight, the Fw, and the vertical component of the force of the rope, the Fv. In other words, how much does Fv reduce that weight force? 450 newtons. Are you kidding me? Okay? And that's what I've got down here. Where's my little cursor thing? Okay? Now I'm going to write in here. You should probably do this. I need to fix this set of notes. The vertical component is going to be FA or F sine theta. Yeah, why is that flashing like that? That's not very nice, is it?
Should we do the right one, not that one?
Yeah, do this. No, do this one first, and then I'll show you how it fits in over here, right? So this is going to be 260 sine 30. I apologize for that flashing. That's just, I got to turn this into a smart file instead of a PowerPoint. 260 sine 30 is 130. Okay? So what I'm saying is that 260 newtons is how much is pulled. Of that 260, 130 is actually lifting up. 130 is actually lifting up. So over here, I've got my normal force is equal to my weight force minus this vertical component, right? And this value here is 130. So I've got 450 minus 130, which gives me my 320. Okay? My normal force is reduced by the vertical component. The normal force is reduced by the vertical component. Okay? So my horizontal component was my 225. It's equal to the frictional force because it's moving at a constant speed. The vertical component we worked out down here, Fa sine 30, we got 130 newtons. There's 450 newtons of weight force pushing it down. 130 newtons is pulling it up, which makes my overall normal force equal to 320. Does that make sense?
Yeah.
I got one yeah. Yeah? All right. That means then I can go ahead and calculate my my frictional coefficient. It's FF over Fn. 225 over 320. The frictional coefficient is 0.703. Okay? Frictional coefficients tend to be less than 1. They could be greater than 1 if there's a lot of friction, but for the most part, they tend to be somewhere between about 0.1 and 1, that kind of thing. How much would that be worth on a test, you think? Something like that.
5.
5? Well, you'd certainly get one for getting the 225.
Okay.
You would get one for the 130. 2. You'd get one for the 320, and one for this. Probably 4.
5 for the diagram.
Depends if I give you the diagram, or if it's part of the question.
5.
Sure, just
7. 7.
Remember that there's no units on mu because the newtons cancel out, right? So we got newtons over newtons, no units here. No units. Okay, here's example number 2.
How about example number 7?
Where's that?
It's on the back. It won't take too long. It's just a little bit weird. A wooden block weighing 130 newtons rests on an inclined plane. The coefficient of sliding friction between the block and the plane is 0.62. So I've given you the angle. Find the angle of the inclined plane at which the block will slide down the plane at a constant speed once it has started moving. There's some magical angle, right? As I raise it up, there's some magical angle. If I go too high, the block's going to do what?
Rip.
It's going to accelerate, right? But there's some angle somewhere where it will slide at a nice, perfect, constant speed. What is that angle?
It's going to rip if you lift it up that fast.
Yeah.
Rip, Mr. Bennett.
One buck. It depends on a lot of different things, right? Now, remember this triangle in here, right? You probably want to draw that little triangle in there. And remember that this angle here is equal to that angle there, right? This angle here is equal to this angle here. That makes a difference. 45 degrees, it says. Possibly. The point at which the block begins to slide is when the force along the incline, the FD, is balanced out by the force of friction, FF. In other words, the FD is exactly equal to FF.
Write that down.
Yeah, that's kind of important. Okay? This is the
Like-
weight force.
Like the words are just,
Well, I mean, that's what it boils down to, right?
yeah.
When it's moving at a constant speed, the FD must equal the FF. Okay? Now remember, the FD is actually this component of this triangle here. It's just that we draw it up there. I didn't draw it to scale very well. Right? And remember, this angle here is the same as the angle down there, right? So we got sine. Do I know my FW? I know how much this block weighs, don't I? 130 newtons?
Yep.
Okay, so I know this. Could I figure out what FD is equal to? Well, it's sine of whatever that angle is, right? Okay, so if I look at this triangle right here, don't write that, don't even write anything down. Just don't write. Put your pens down. Watch. Watch, watch, watch. Watch, watch, watch. I'll give you a chance. Watch. Okay? In this triangle right here, opposite is FD, adjacent is
Okay.
Fn. So opposite over adjacent is tan. Tan theta is equal to FF over Fn. But what else is equal to FF over Fn? So tan theta is simply mu, right? Tan theta is equal to mu. The mu value was 0.62, so to get the angle, I just take the inverse tan of 0.62. That's all I have to do.
This question is the first one.
I'll let you write it down, then I'll explain it again. So, we know that this block will begin to slide at a constant speed when the FD and the FF are equal. Okay, so I look at this triangle that I've drawn here, and I can see that I've got my FD and I've got my FN. Okay, and I don't know what they are yet, right? And this isn't something that you would just go, oh yeah, I get that. I mean, I know to do that. You're not going to just know to do it. That's why I'm showing it to you. Okay, but I'm showing you why it works. So I've got my FD and my FN. If I go opposite over adjacent, then that's equal to tangent, right? So tan theta is equal to FF over Fn. But what else that I've just shown you is equal to FF over Fn? Mu. I can replace FF over Fn with good old mu, which we know to be 0.62. So I've got tan theta equals, I mean, if you want, you could put in here tan theta is equal to 0.602, and then you just do that second function thing. Right? Tan theta is equal to 0.602. Theta equals the inverse tan of 0.602, 31.8. And oddly enough, and you don't need to write this down, but you should be aware of it. In other words, the block will slide at a constant speed when the angle of the incline is 31.8 degrees, no matter what the block weighs. How come I can say that? Did I ever use the 130 over here?
No.
Never used it. Could be 1,000. Could be 2,000. 10,000. It's not going to matter because it's only FF over Fn. It's only the 0.62. No matter what the block weighs. If the angle is greater than 31.8, the block will accelerate down the plane. Now, having said that, though, you still need to, if I put the ramp at 31.8, the object wouldn't move until I gave it a little push, because remember, starting friction and sliding friction are different, so we're talking about sliding friction. So you have to get it going, and then once you got it going, then it would continue at that constant speed. Okay? I will shut up now, because I know you're tired of me. I said yes. You've got... Oh, I didn't give you that package.
60 seconds.
Okay, so you got friction questions, you got non-friction questions on an inclined plane from yesterday, you got net force. Tomorrow's a work period. Monday, we'll do the frictional coefficient lab. So come Monday, ready to rock.